Okay, so we're doing this example from last time. So, let's talk about the test. So, exam 2 is Friday. And I think it is reasonable to do so the topics for this are going to be all of stresses and beams. Well, everything before that too, up through stresses and beams. Okay, anybody have any questions about the test? Anything related to that? The last topic that we have in stresses and beams is shear stresses due to torque, to torsion. So we're going back to talking about that. Oh yeah, but just to clarify, because I know this is important to you. So like I studied like crazy, like I totally studied like crazy, but I just for some reason never liked sitting in class. I think like it always moved like a little faster than I wanted it to. So I felt like I was just there taking notes. And then I get back and I'm like, my notes say what the textbook says, Well, I should just spend that time reading the textbook or whatever. So anyways.
Read the textbook and then go to...
Yeah, I could have done that, but I didn't do that. I would do a lot of things differently if I could do it all over again now.
I think you never go to class at all because you know the material.
That's true. Okay, so for circular cross sections, we had that the shear stress in that temporary coordinate system, the XY shear stress, is equal to negative torque times the distance that you're looking from the centroid divided by the polar moment of inertia. Mm-hmm. And for thin-walled tubes, you have negative torque divided by 2 times the thickness times the median area. Okay, so those are the two things, and we're in the middle of an example where we could use both of these two methods. So we're doing this for a thin-walled circular cross-section. Where it looks like this. This is our outer. This is our inner. And we did the one for the thin-walled tube, I think, right? So what we got was the tau xy was equal to negative 2t over pi times the quantity r outer cubed plus r outer squared times r inner minus r outer times r inner squared minus r inner cubed. And so now we're going to do it for a circular cross section. We have to calculate the, so we have that this shear stress is equal to negative T times rho over I sub P. So we have to calculate this polar moment of inertia. And that is the polar moment of inertia of the outer radius, using the outer radius, minus the polar moment of inertia for the inner radius. So you could think of this as polar moment of inertia outer minus polar moment of inertia inner. And so this comes out to be pi over 2 times the quantity r outer to the fourth minus r inner to the fourth. And so the polar moment of inertia, we can write this as, why did I do it like that? Well, let's just write it as, okay, so we're going to get this torque xy, or this shear stress, is equal to negative torque. Let's do this calculation at the outer radius, and then it's divided by this thing. Since dividing is the same thing as multiplying by the reciprocal, so the 2 is going to be in the numerator. And in the denominator, we have pi times r outer to the fourth minus r inner to the fourth.
So the rho is r outer in this case?
Yeah, I mean, we could change that to, so remember that, I think in the example, I said that that's what we're trying to calculate the stress here. Okay. And so let's plug some values in here. So let's say that first, we're going to say our outer, let's make that 5 centimeters. And let's say that the wall thickness is 1 millimeter. Okay, so our inner is 0.499.
.049.
Yes. Okay, so let's do it for the thin-walled. So we have tau xy is equal to negative 2t divided by pi times 0.05 to the third plus 0.05 squared times 0.049 minus 0.05 times 0.049 squared minus 0.049 cubed. And so, let's see. So I'll write this as negative 2 divided by pi times 0.049. And so we get a stress that's equal to negative 5,091.2 times that torque. Anyone else calculate that? You get the same thing? And now we'll go to the circular. And tau xy is equal to 0.05 to the fourth power minus 0.049 to the fourth power and oh my god, I messed up that other calculation really bad. 0.02. Okay, so I got, for the circular one, I got 1.312 times 10 to the 6 times the torque. And I have to enter the other one in again. Oh, and shoot, I'm messing all this up. Okay, so for the circular one, we also have a 0.05 in the numerator. Okay, so here we go. So for the circular one, we get negative 65604 times the torque. And for the thin-walled one, we get negative 64954.6 for the torque. So you can see percentage-wise, those are super close, but that's a really thin wall, you know. That's a millimeter thickness, which, by the way, you know, steel tubes are surprisingly thin for whatever application you're using. Like if you can picture an old, like a bike that you find in a garage sale with a steel, the thickness of those tubes is right around a millimeter, you know, and it feels like a pretty substantial thing. And it's not like it flexes if you try to flex it, you know. So a millimeter can support, you know, a tube with a millimeter thickness can support a lot of load. But so there you go for that. But now, like, what if the wall thickness is 0.5 centimeter, you know? So let's do that again. So this is going to be 0.005 meters. And so I said a rule of thumb is that the thickness is less than 1/10 of the total dimension. So now we're right at that value, right at 1/10. So we'll see how they change. One thing about this is at the outer wall, okay? So if you're using the thin-walled approximation, if you're using the thin-walled tube approximation, what would you get for calculating the stress at the inner wall? This is a trick question. You get the exact same thing. We don't make any distinction as you go through the wall thickness.
But technically, like if you were to, should it be?
It should be a little lower because if you look at this, so, you know, well, I can tell you what it would be if at the inner wall, it would be 6.4. So if you use the circular calculation and calculated the stress at the inner wall, it would be 64291. So somewhere in between the inner and the outer wall, this circular calculation matches the thin-walled approximation. Okay, but the thin-walled approximation assumes that it's the same all the way through the thickness. The circular approximation assumes it varies by that rho value as you go through the thickness.
Yeah.
Okay, so now we're going to do it for this bigger value. So for the thin-walled, okay, so what was the percentage error here? So let's say we have 65,604 minus 64,954.6. divided by 65,604. And you get about 0.9% error. Okay, everyone would say that's good. You know, this one isn't nearly as good as the wall thickness gets bigger. So you got 14,809.4 minus 14,107.9 divided by 14,809.4, and you get about 4.7% error. Okay, and this is, so when I told you 10%, the wall thickness, 10% of the overall width, I said that this was okay, you know, so I'm saying 5% error or whatever, we'll take that, but we don't want to go bigger than that, you know. This is clearly fine because we're talking about a 50th. Okay. And again, if you're using the circular cross-section calculation, the stress absolute value gets bigger as your rho value gets bigger as you get away from the centroid. Okay, and so if you use that calculation to determine the stress at the inner wall, you'd get something that was less than the thin-walled approximation in absolute value, you know what I mean? So no matter what the thickness of the wall is, using the circular calculation, you're always bracketing the value that you get in that thin-walled approximation. Are you with me on that?
Yeah.
Okay. Okay, well that's it for stresses. I mean, let's just go through a big calculation with everything. Well, what are we capable of calculating? There are two possibilities. First, what if we wanted to have a circular cross-section? What are our, what calculations could we do?
It has to be at the neutral axis.
It has to be on the neutral axis, that's exactly right. So a circular one we can do, whether it's solid or thin-walled or whatever, we can do that with everything, but it has to be on the neutral axis. The only other thing that we can do is
Thin-walled rectangle.
Thin-walled rectangle, and that we can do everywhere. So let's do that, why not?
So I have actually a quick question.
Yes.
So like circular along the neutral axis, it looks like we've had some stresses that depend on like your lateral.
Yeah, only the torque.
Okay, so, okay.
And so yeah, what you do then is you calculate it in that temporary coordinate system and then do the rotation. Use the rotation matrix to put it in your regular. And then once you have your stress due to tension, bending moment, shear force, and torsion, and you have them all expressed in your desired coordinate system, then you finally just add them up and that's your stress tensor.
Okay, so if we were given a beam that only had tension, bending moment, and shear force, it wouldn't make sense to define a point.
Oh, that's right. The torque is the only one of these internal loads that matters where you are horizontally. Everything else only matters vertically. Yep, that's perfect. Okay, let's just do an example, start to finish. I've been lazy with these, with the reaction loads with the joints that are holding these things, and I'm going to continue with that because I'm sick of calculating external loads. So we're just going to put this thing like this. Okay, and we're going to say that there's a force this way of 10,000 newtons, a force this way of 5,000 newtons. The beam has a length of 2 meters, and the mass is, well, let's get the mass in a second. And then let's apply a torque to it this way of 1,000 Newton meters. And the cross section. Okay, so
This is square in wall two.
what?
Is it in wall two?
Yeah, we're going to have to do a rectangular thin-walled tube. And
That's the only thing you do all.
it's the only one where we can do all of them at every point on the cross section. And let's do a calculation here. Okay. Well, let's give dimensions. Let's call this 10 centimeters.
That line is so straight.
Thank you.
I think it's
Ah. Let's call this 5 centimeters. And let's say the thickness is it looks like the thicknesses are different everywhere, but let's say it's the same everywhere. And let's go with 5 millimeters. Okay, so we know we're going to be, with this approximation, using a thin-walled tube for the torque, we could be off by 5% or whatever, but that's just, we're going to accept that. And now let's figure out what the mass is. Okay, so this material is, let's say, is steel. Steel has a density of about 7,000 kilograms per cubic meter. Okay, so let's calculate the volume of steel we have and see what the mass would be about. So the volume is the area of the cross section times the length. So the area of the cross section is 0.1 times 0.05 minus 0.095 times 0.045, and then multiplied by the length. Why did I get a negative answer? That should not be.
You have to take the thickness off of both sides, so it's not 0.495, it's 0.49 or 0.49.
You are right, thank you. Although I still don't understand why I have negative. Oh, I understand why. Times 2, okay, times 7,000, the density of steel. And so this thing has a mass of about 20 kilograms, almost exactly 20 kilograms. How many cuts do we need? So we're trying to calculate the stress tensor here. Oh, and actually, you know what? Let's calculate the maximum shear stress. at this point P. Okay, so let's roadmap this. What are we going to do? Oh, and I have to choose a point, let's say at the wall. That's, in a cantilever thing, that's almost always where you're going to have the biggest problems, is the connection to the wall. Okay, so what are we going to have to do as a roadmap? We're going to have to calculate the internal loads at the wall. Okay. Then we're going to have to calculate the stresses due to tension, bending moment, shear force, and torque, and add those up to get a stress tensor. Then we're going to have to calculate the principal stresses. And then from those principal stresses, we're going to calculate the maximum shear stress. Okay? How many cuts do we need? Yeah, so cut 1 is good for all the x's from 0 to 2. I'm going to start out by writing out the distributed load for the mass. We have a 10,000 Newton force here. A 1,000 Newton meter couple, a 5,000 Newton force down, a distributed load due to the weight. What's that distributed load going to be? Well, the total weight is 196.2. That's spread out over 2 meters. So we get a value of 98.1 newtons per meter. And then we have our internal loads: tension, shear force, bending moment, and internal torque. And from that distributed load, we have a length of x and a height of 98.1. So the total point force is 98.1 x. So I'll redraw this now. We have a point force at the middle of 98.1 x. You can see how, I mean, I pulled these numbers out of thin air, but you can see these are kind of in the ballpark of what seems reasonable for external loads. This, we actually calculated a reasonable mass, and you can see how much that weight force is going to be dwarfed by those other forces. That's why in a lot of cases you end up just leaving the weight out of this stuff. It just doesn't matter to any in the calculations. We got the 10,000, the 1,000. I'm just writing the Newton meters to remember that's a torque. The 5,000 here. And then the internal tension, shear force, bending moment, and torque. Newton's second law. Well, actually, I'm just going to calculate it. I've drawn all these pictures. Let's just calculate it. But since all we're looking for is we're looking for what's happening at the wall, there's not really any reason that I had to come up with internal loads as functions. I could have just done the cut at the wall, you know what I mean? And just gotten those. I mean, yeah, that's what we're going to do now is, right, exactly. Instead of treating this as 98.1x, yeah, you could just plug in your 2 for everything and just get values at the wall. But I'm already committed here. So we have 10,000 in positive x, 5,000 in negative y, plus 0, negative 98.1x. 1, 2, plus t negative v is zeros. So t is negative 10,000. Is that tension or compression? Compression, yep. And v is negative 98.1 x minus 5,000. And then the moment equation about the x-axis, we have negative 1,000 plus fancy t is equal to 0. So the internal torque is positive 1,000. And then the moment equation about the z-axis, our about point is over here. So we have a clockwise moment of x over 2 for a moment arm times the force of 98.1 x plus m minus vx is equal to 0. So m is equal to positive 49.05 x squared plus vx, so minus 98.1 x squared minus 5,000x. And so the bending moment is negative 49.05 x squared minus 5,000 x. Well, one thing is if we did if we just did a cut exactly at the wall and just calculated those point values, we couldn't use our derivative checks. So I guess that's one positive of doing the whole thing like this. Now we can because we have functions. So dm dx is equal to v. That's good. Negative dv dx is positive 98.1, and that's our distributed load function, so that's good. So now at x equals 2, we have an internal tension of negative 10,000, an internal shear force of, that's negative 5196.2. An internal torque of positive 1,000. And an internal bending moment of negative 10,196.2 Newton meters. That's a huge frickin' bending moment. That's going to rip this thing off the wall. So like you could tell your boss that without doing the rest of the calculations, but okay, but we're going to do it anyways. That's the internal load. Let's stop there and we'll just go through all the stresses on Monday. Okay. All right, that's all. Have a good weekend.
So, the exam of this class is done next Friday.
Yeah.